All right, so we're jumping over section 4.2 and we're into 4.3 right now. We'll go back to 4.2. We're talking about right angle trig. And trigonometry, the base for trigonometry, trigon just means a triangle, and metry comes from meter, which means to measure. So basically we're talking about measuring triangles is where trigonometry comes from. So let me get a triangle up here, and we're going to be referring back to this picture a lot. Here's my right triangle. So for these right triangles, here's my right angle, and we'll call this angle theta. And for everything that we're talking about today, our angle theta is less than 90. So we're going to say that 0 less than or equal to theta less than or equal to 90 degrees. So we're talking about acute angles for everything that we're talking about today. The way we're going to label this triangle is our angle that we're interested in, theta, is our kind of our reference angle in our triangle. This is going to be the opposite side. This is the adjacent side. And this side is the hypotenuse. So whenever we're talking about trigonometry, this is how we're labeling our triangle. Because if we have a particular angle in a triangle, in a right triangle, no matter how big or how small that triangle is, as long as it has this particular angle and a 90-degree angle, all angles with a 90-degree angle and some other angle are going to be similar. So we can make these ratios between the sides, and they're going to be the same no matter how big that triangle is. And that's really the foundation of trigonometry, is that all right triangles with a particular angle are similar. So no matter how big or small they are, we can make these ratios. So we're going to define our trigonometric ratios. We say the sine of theta is the opposite over the hypotenuse. And I'm going to use a shorthand here. Opposite over hypotenuse. The cosine of theta is the adjacent over the hypotenuse. The tangent of our angle is the opposite over the adjacent side. And no matter how big or small our triangle is, as long as we have this particular angle in a right triangle, we're always going to have the same ratio. That's what lets us work with, that's what makes trigonometry work. Now we're going to define what we call our cofunctions. Our cofunctions are the reciprocals of these. So our reciprocal of the sine is called the cosecant. Cosecant of theta is the hypotenuse over the opposite. Our secant is the hypotenuse over the adjacent. And the cotangent is the adjacent over hypotenuse. And if you probably, for the sine, cosine, and tangent, you probably remember SOHCAHTOA to remember sine, cosine, and tangent. SOHCAHTOA is how you can remember those. And then the cofunctions, we call the cofunctions, are just the reciprocals of those. So the cosecant is the cofunction of the sine, the secant is the cofunction of cosine, and the cotangent is the cofunction of the tangent. Oh, did I? Yes, it should be adjacent over opposite. Thank you. Nice catch. And if we restrict our angle, if our angle is between 0 and 90 degrees, if theta is between 0 and 90, all of our trig functions, sine, cosine, and tangent, all come out to be positive numbers. If we restrict our angle, all of our trig functions come out to be positive numbers. And again, just a reminder, this is, to get this side, I just took the reciprocal of this side. A couple of things to remember about the trig functions, and it's mistakes that people make every year when we talk about trig functions. When we're talking about the sine of theta, the sine is, we're thinking of the sine as a function. So what we really mean is, if we were being more precise, we would write the sine of theta, like we write f of x. Because what will happen is students will have something where we have a problem like sine of theta divided by theta, and then you want to cancel theta and say that just equals sine. We can't do that. So I'm just going to say no, we can't do that. So the theta is what goes into our function. We're not multiplying. It goes into our function. And the type of problems that you'll see, the right angle trigonometry is, an example might be that we're given a triangle and we're given one side, and we want to find, or we're given two sides, and the problem will tell us to find the exact values of the 6 trig functions for this particular angle. So let's look at an example like that. So our example is, if we have this triangle, there's our angle, and we know that this side is 15 units long and this side is 8 units long. The problem will say find the exact value of all 6 trig functions. So we have a couple of tools that we're going to work with. We have a right triangle. What I recommend, if it helps you out, is to label all of your sides. So this is my angle. 8 is going to be my opposite, adjacent, or hypotenuse. That's my adjacent side. This is the opposite side. Hypotenuse is always the longest side. So if that helps you out, label your triangles, label your sides. Now we're missing the hypotenuse. What can we always use on a right triangle? A squared plus b squared equals c squared always works on a right triangle. So let's call this side C. Our hypotenuse is C. So we know that c squared equals 15 squared plus 8 squared. So c squared, I did my square root too early, is 225 plus 64. So c squared is 289. And c is the square root of 289, which for this particular problem turns out nice. Turns out to be 17. So the hypotenuse is 17 units. Now we have all 3 of our sides. We can write all 6 of our trig functions. And when it says we want to write the exact value, what is it telling us? Leave it as a fraction. Leave it as a fraction. When it wants the exact value, leave it as a fraction. It doesn't want a decimal approximation. If the problem said, write the approximation of the 6 trig functions to 3 decimal places, then you would plug it in your calculator and write decimals. For this one, we want the exact value. So the sine of theta is opposite over hypotenuse. So we get 15 over 17. Cosine of theta is the adjacent over hypotenuse, 8 over 17. Tangent of theta, opposite over adjacent, so 15 over 8. And then for our cofunctions, we're just going to write the reciprocals. So the cosecant is 17 over 15. And the secant of theta, 17 over 8. And the cotangent is 8 over 15. So we found that third side and we were done. And we could do that because the Pythagorean theorem always works on right triangles. Questions on that? Okay, so there are a couple of right triangles that are especially important in trigonometry because of the way that the sides of those right triangles work. So we're going to look at 45, 45, 90, and 30, 60, 90 triangles and spend a little time with those because when we start working with the unit circle, those are extremely important triangles. So let's look at a 45, 45, 90 triangle. All right, so here's my 45, 45, 90. See if I can get a decent looking one here. That's pretty good. So we are going to, we're going to say each of these is 45 degrees. And just to make our lives easier, we're going to say that each of these sides, because the two angles are the same, the two sides are the same, each of those sides is 1. Just to make our calculations easier. If each of those sides is 1, how long is the hypotenuse going to be? If this is c squared equals 1 squared plus 1 squared. So c squared equals 2. So c equals square root of 2. So on a 45, 45, 90, if the side lengths are 1, the hypotenuse is square root of 2. And that works for 45, 45, 90 no matter what the side lengths are. These two sides are always the same. The hypotenuse is square root of 2 times the side length. So let me draw another 45, 45, 90. This is going to be important to remember. If this is a 45, 45, 90, thank you. If these two sides are x, the hypotenuse is going to be x times the square root of 2. Hypotenuse on a 45, 45, 90 is always square root of 2 times the length of the legs. So using this 45, 45, 90, we'll use the one with the side length 1 to make our lives easier. We can write the sine, the cosine, the tangent. We can write all of our trig ratios for 45 degrees. So let's write our ratios for 45 degrees. So the sine of 45 degrees is the opposite over hypotenuse, so 1 over square root of 2. And when we have a square root in the denominator, we always like to rationalize the denominator. So to rationalize our denominator, remember what we do? To get the square root of 2 out of the denominator? Anyone? Close. Multiply top and bottom. So we want to multiply top and bottom by square root of 2. So you're almost there. So multiplying both sides to rationalize the denominator, we multiply by whatever this radical in the denominator is on the top and the bottom. Square root of 2 over square root of 2 is just 1. So what we're doing here is just multiplying by 1. But what this lets us do is write 1 times the square root of 2 is square root of 2. Square root of 2 times the square root of 2 is 2. So the sine of 45 degrees is the square root of 2 over 2. No matter what length the sides of the triangle are, the sine of 45 degrees is square root of 2 over 2. The cosine of 45 degrees is the adjacent over hypotenuse, which is also 1 over square root of 2, which is square root of 2 over 2. So the sine and cosine of 45 degrees are both square root of 2 over 2. And in radians, what did we decide 45 degrees was in radians? How many radians? Pi over 4. So the sine and cosine of pi over 4 is square root of 2 over 2. The tangent is the opposite over adjacent, just 1 over 1 or 1. So the tangent of 45 degrees is 1. These relationships show up over and over and over and over in trigonometry. You should work on memorizing these. Sine of 45, cosine of 45, tangent of 45. They come up all the time in trigonometry. And the reason we use them is because they do turn out nicely. So we tend to use 45 degree angles, and we'll talk about 30, 60, 90 triangles in just a minute. Everybody good with how we came up with the sine, cosine, and tangent of 45 degrees? Picture perfect? Okay. So a lot of times, before we move on, a lot of times people ask, why do we rationalize the denominator? Why don't we write 1 over square root of 2? Well, there's nothing wrong mathematically with writing 1 over square root of 2. My explanation is, do we have an idea of how big square root of 2 is? Anybody have an estimate of what square root of 2 is? Is it more than 1? Yes? No? Is it less than 2? 2 squared is what? 2 squared? 4. So it has to be between 1 and 2, right? The square root of 2 is somewhere between 1 and 2. It's easier to think about how big a number between 1 and 2 is. 1 and 2 divided by 2. So 1 point, it turns out to be 1.14. It's easier to think about 1.14 divided by 2 than it is to think about 1 divided by 1.14. It's hard to think how big 1 divided by 1.14 is. It's a little easier to think 1.14 divided by 2. You have a better idea of how big that number is if you write it this way than if you write it this way. So that's my explanation, is it gives you more of a feel for the size of this number. Square root of 2 over 2 is about 0.707. So we have a better idea. It's easier to see that than to think about 1 divided by the square root of 2. So that's one reason why we rationalize the denominator. Another reason is just it's kind of convention. So if everybody does it the same way every time, we always end up with things being kind of the same, no matter who's doing it. That's another reason we rationalize the denominator. All right. Part of what we're going to do today is work with 45, 45, 90 triangles. So I just want to remind you how to go back and forth between the sides of the triangles. So my shorthand here is to go from a side to the hypotenuse. We multiply times the square root of 2. Go from the hypotenuse to the side, we divide by the square root of 2. So that's how we go back and forth if we know one or another side of the 45, 45, 90 triangle. All right, we're ready to look at 30, 60, 90 triangles? All right, 30, 60, 90s. So let's draw a 30, 60, 90 triangle. Here's going to be our triangle for this one. This is our 90-degree angle, our 60-degree angle, and our 30-degree angle. And for this one, we're going to say the shorter side has a length of 1. The shorter side is always opposite the smallest angle. So the shorter side of our 30, 60, 90 is always going to be opposite the 30-degree angle. We'll call this the longer side, always opposite the 60-degree angle, and this is the hypotenuse. Now, does anyone remember how the short side and the hypotenuse of the 30, 60, 90 triangle are related? I'll give you a hint. A 30, 60, 90 triangle is half of an equilateral triangle. The hypotenuse is double. So this would be one side of the equilateral triangle. This would be half the side. So if our short side is 1 unit long, our hypotenuse is 2 units long. Anybody remember how the long side is related to the short side? It has to do with square root 3, but rather than the 2, it's just the short side times square root 3. So this is going to be the square root of 3 units long. We could do this, we could figure this out. Once we knew these two, we could figure this out with the Pythagorean theorem. So this relationship is going to hold for any 30, 60, 90 triangle. So let me, yes, Colin. Oh, you were just gesturing? Yep. Okay. So let me draw another one. Our general 30, 60, 90 triangle. If this is our short side, this side is going to be the short times the square root of 3, and this is the short times 2. So no matter what the side lengths are, these relationships are going to be true in a 30, 60, 90 triangle. And the diagram that I drew for the other triangle, we multiply by the square root of 3, or multiply by 2. To go the other way, we just divide. Divide by the square root of 3, or divide by 2. The short side is the key on a 30, 60, 90 triangle. So this is going to be true for any 30, 60, 90 triangle, these relationships. The hypotenuse is twice as long as the short side. The long side is square root of 3 times the length of the short side. So we'll use this to write our sine, cosine, and tangent of 30 degrees and 60 degrees. So we'll look at the 30-degree angle first. The sine of 30 degrees is opposite over hypotenuse is 1/2. The cosine of 30 degrees we're looking at the 30-degree angle adjacent over hypotenuse is square root of 3 over 2. And the tangent of 30 degrees is opposite over adjacent is 1 over the square root of 3. And if we rationalize that denominator, we get the square root of 3 over 3. Let's look at our cosines. Or, I'm sorry, not our cosines, our 60-degree angle. The sine of 60 degrees. Now we're looking at this angle, opposite over hypotenuse, square root of 3 over 2. The cosine of 60 degrees is adjacent over hypotenuse, 1/2. And the tangent of 60 degrees is opposite over adjacent, or just square root of 3. Does anybody see a pattern here, something that looks interesting? Sine of 30 degrees is the same as cosine of 60 degrees. Cosine of 30 degrees is the same sine, is the same as the sine of 60 degrees. How are 30 degrees and 60 degrees related? How did we talk about them the other day? What do they add up to? 90. So they're complementary. 30 and 60 are complementary. When angles are complementary, the sine of one equals the cosine of the other. So when we have complementary angles, the sine of one equals the cosine of the other. And that will be true of any complementary angles. And the way that we can write that, this relationship between the complementary angles, is that the sine of 90 degrees minus theta equals the cosine of theta. The cosine of 90 degrees minus theta is the sine of theta. The tangent of 90 degrees minus theta is the cotangent of theta.
Wait, this one's the base of 2 angles?
This is true for any two angles that are complementary. If two angles are complementary, their sine and their cosine are the same. Because if we have some angle theta here, its complement is 90 degrees minus that angle. So no matter what that angle is, this 90 degrees minus that angle would be the complement. So the sine of the complement equals the cosine of the angle. So if angles are complementary, the sine of one equals the cosine of the other. And that's true for the cofunctions also. So the sine of the angle equals the cosine of the complement. And that was, we can see that with 30, 60, 90. So the relationships with the 45, 45, 90 and 30, 60, 90 triangles, they show up so often in trigonometry that we should work on memorizing these. The sine of 30 degrees is 1/2. Cosine of 30 degrees, square root of 3 over 2. Tangent of 30 degrees, square root of 3 over 3. So we'll work on memorizing those. When we start working with the unit circle, these relationships are going to come up over and over and over. 30 degrees in radians. You remember what 30 degrees in radians is? Pi over 6. So 30 degrees, pi over 6. 60 degrees in radians, pi over 3. Perfect. So we'll start working on those when we work on the unit circle. We'll work on those a little more. All right, only one last thing I want to talk about really quickly, and that has to do with your calculator. When we're working in trigonometry, make sure that you pay attention to how they give you the angle in the problem. If the angles are in degrees, you have to have your calculator set in degree mode. If the angles are in radians, you have to set your calculator in radian mode, or you'll get the wrong answer. So let me show you that. So on your calculator, as soon as this comes up, all right, to change from degree to radian, you're just going to go to mode here. Right now, this calculator is set in radian mode. So if our angles were in radians, I would want my calculator set in radian mode. And if we find the sine or the cosine of some angle in radian mode, if our angle's in radians, we find the sine or cosine, that's going to give us the right answer. To change the mode, I'm just going to toggle down to there. Go over to degree, hit enter, and now my calculator's in degree mode. So I would use degree mode if the angle's in degrees, use radian mode if the angle's in radians. If the problem gives you an angle in radians and you're in degree mode, the answer that you get from the sine or a cosine is going to be crazy. It's not going to make sense in your problem. So make sure your problem is set to the right mode depending on what the problem is asking. Now the thing that I wanted to remind you of is how we find an angle if we have the ratio. So finding an angle. So this is going to be important. We're going to be doing this a lot, finding an angle from a ratio. An example of that is if the problem says we have the sine of theta equals 0.357. And we want to know what our angle is. Do we remember how to figure out an angle if we know the sine of the angle on our calculator? Remember what to do? We have the ratio. This is the ratio. We want the angle. Inverse sine. To find the angle, if we know the ratio, we use inverse sine. On the calculator, it's sine minus 1. So I'm going to put 357 in my calculator. I'm going to do 0.357. I'm going to do inverse sine. Oops, I did it backwards. Do inverse sine of 0.357. And that tells me it's 20.91 degrees. My calculator is in degree mode, so my answer would be in degrees. I guess I'd round this to 0.92. So the inverse sine of 0.357 is 20.92 degrees. If my calculator were set in radian mode, my answer would be in radians. If I had it in radians mode, I did that calculation, I would get that it would be about 0.356 radians. So if my calculator were in radian mode, it would tell me this answer in radians. In degree mode, it tells me the answer in degrees. So when we're doing this more, it's really important that you have your calculator set in the right mode. Same goes for cosine or tangent. If they give you cosine of an angle and they want the angle, you have to use the inverse cosine or inverse tangent. And one final thing, if you get a problem like this, you might have some kind of surveying problem or something to do with the globe like we worked on the board today. And it says it wants the cosine of 16 degrees, 18 minutes. How are we going to go about figuring this out? Convert this to decimals first. So you're going to convert to decimal first. And then plug it in your cosine. So if you get a problem where you have to find the cosine of some angle that's in degree, minutes, seconds, you have to convert it to decimals first. And then find the cosine or the tangent or the sine or whatever they ask you. Is everybody good? Okay.